Let's do another example of a KSP calculation. This one is of a salt that has a 1 to 2 relationship between its ions. We have 1 zinc, we have 2 hydroxides with it. And again, we have a very similar KSP reaction. We just have a salt, solid, dissolving, and when it dissolves, it'll break into its respective ions. So zinc 2 plus and 2 hydroxides. Now, we can determine the concentration of zinc and hydroxide in this solution. Now, in this case, because whenever one of these zinc hydroxides dissolves, 1 zinc is made and 2 hydroxides, the end result will be that there will be a higher concentration of hydroxide in the solution at equilibrium if we just put this particular salt in a solute in water to let it dissolve. So this is also a fairly insoluble salt. It has a KSP of 3 times 10 to the minus 17, so this is quite insoluble. But let's see how what the actual concentrations are. So if we start off, we have 0 zinc and effectively no hydroxide. Let's see what happens. Now we'll make X amount of the zinc and we'll make 2X amount of the hydroxide because we have 2. And then 0 plus each of those will lead X and 2X. Now let's take this and put it into our equilibrium expression. So our equilibrium expression will be zinc concentration times hydroxide concentration squared, right? Because we have a 2 here. Now, you'll also notice that in this example and in the previous example, I didn't talk about how much of the solid is actually there. Now, it is generally assumed that there's enough solid there to form a saturated solution. That is, all that can dissolve is available, right? We're not limiting ourselves with how much we're putting in of this salt. But beyond knowing that there's enough to saturate the solution, we don't actually need to know how much is there. It's just not important. Nowhere in our K expression does zinc hydroxide appear since it's a solid. So it's not important to know how much is there, other than making sure there's enough to fully saturate the solution. All right, so let's plug in our equilibrium values, which is just X and 2X. So we're going to have X amount of zinc, and we're going to have 2X of hydroxide, which is squared. Now, please be careful. The 2 is also squared. So when we do the calculation here, 2 squared, that's 4. So this is really 4x squared, not just 2x squared. So just be aware of that. So 4x squared times x, that's really 4x to the third power, right? 2 from there, 1 from there. And that's going to equal my 3 times 10 to the minus 17, which is the value of KSP. Now we can solve that for x by dividing both sides by 4 and raising it to the power of 1/3. So if you're putting this in a calculator, one way to do it is to take your value, put the little to the power button, and then a parenthesis 1/3, close the parenthesis, you're good. And if you do that, you should get x equal to 1.96 times 10 to the minus 6. And this will be the concentration of zinc. Now, if we remember up here, this is 2x, so if we actually want to know the concentration of hydroxide, we'll just simply multiply this value by 2 to get 2x. So that is 3.92 times 10 to the minus 6, and that's molar hydroxide. And since this is a hydroxide and that's an acid-base thing, if we wanted to, we could actually determine the pH. This is a base, and so we should expect a basic pH, and indeed we do have one. pH of that solution is 8.59, and that does match with our expectations. Since this is a base, that is slightly above pH 7. Now, we don't expect it to be very basic because, again, the KSP is quite small, so very little of this is dissolving. One of the things that we could do to make this particular salt dissolve more would be to add acid to it. And if we did, that would effectively remove the hydroxide from solution, and that would drive the equilibrium forward because it would need to replace what was lost over here. That would increase the amount of zinc in solution as we're using this up. Of course, you'd be changing what is actually the ion in solution to be the new counter ion of the strong acid, or I suppose a weak acid may work if it was reasonably strong, but certainly a strong acid would dissolve this much better. For example, if we used nitric acid, then effectively we would be making zinc nitrate in the solution. So that's one way to synthesize some salts. So this is another KSP calculation, but again, with a different ratio between the two ions. It's possible to do any number of these. Some reactions will have 2 ions for the positive one. It might have 3 for the negative one. Those get a little bit more complicated, but still it's the same process. Just be aware that when you're plugging in the equilibrium values, that you are careful when you have exponents on there to make sure that you also distribute the exponent to everything inside, and that you distribute it correctly. If, for example, you have a 3x, it will be raised to the power of 3, and you may be tempted to write 9x to the third when really it's 27, because 3 cubed is 27. So be mindful of that. That's a mistake that I've made in the past that I later did catch.